Welcome back. As promised, we're going to do a drill. So here it is. Please write some Python code that estimates the weighted least squares fit of the model parameters where the weighting is proportional to the distance of each point xi, yi from the origin using the following equation. So the weight, again, for every data point indexed on I, is going to be 1 plus the distance of the point from the origin, which of course is just the Euclidean distances, the Euclidean distance, which is the square root of x squared plus y squared. So how do you interpret this? So if the point is exactly at the origin, then what happens? Well, that's 0. 0 plus 0, square root is 0. The weight is 1. What happens is that point starts to move away from the origin in any orientation. Well, that value goes up. And then I add that value to 1, which means the error the weight associated with it increases, which means the error of that point is going to matter more to the weighted least squares estimation. And so the line is going to want to go through points that are far from the origin more than points that are near the origin, regardless of where they are. All right, I'm going to give you this code. It's all on the course website. We're going to import a couple of libraries. I'm going to generate some data, and I'm going to display the result, the data, and your fits. So 10 data points, generate some random x values, generate a random y value corresponding to the model. So here's the model that I mentioned here. It's some value times x plus another constant. So obviously that's a line, first order polynomial. Add a little bit of noise to the data, and you can multiply. If you put a little scalar value there, you can make the noise bigger or smaller. Now, I'd like you to do two things here. Please do a least squares and a weighted least squares estimation, and please generate a vector, let's see, where is it? A vector u, which is going to be the least squares estimate, and the vector uw, which will be the weighted least squares. In u, the first component is the slope, the second component is the intercept, and same for the weighted least squares. So if you generate u and w in your code here, then this display code will work. So you should do two things. Do the standard least squares. You've already done that, so it's just a good exercise to do it again. And then using that as the weighting, please do a weighted least squares and then compare the data. And again, by playing with the amount of noise here, you'll be able to see the difference between the weighted least squares and the least squares. All right, go ahead and pause the video, and when we come back, I'll show you my solution. All right, let's see what we have here. Importing, generating data, displaying. So least squares, weighted least squares. All right, least squares is pretty straightforward. We know how to do this now. I'm going to build a matrix X, which is n by 2. The first column are all the x values. The second column is 1. So x1, x2 to xn, 1, 1, 1, 1, 1. That's going to multiply the slope and the intercept. And my y vector is, well, that's just the data, so I don't have to do anything. And then my least squares estimate u is just x transpose x inverse times x transpose times y. Slope, intercept in that vector u. Good. Now, weighted least squares, I just got to build that weighting matrix, that diagonal n by n weighting matrix. So the weight associated for every point is going to be x squared plus y squared square root add 1. So notice one of the nice things about using NumPy, by the way, I don't have to do this in a loop. So I can write 1 plus a vector, and it will add 1 to every component of the vector. So I square the x's, I square the y's, which come from up here, I square root that, add 1, and now I have a vector of weights that tell me how far something is from the origin. I'm going to build a diagonal matrix, big W, with that on the diagonal. And now I'm going to multiply that matrix by itself in order to get W2, which is the square of the weightings, which is what I need to do the least squares estimate. By the way, I could have skipped this step and just squared the value of W here and put it in the diagonal. I just did this to make it explicit. And now, it's basically this line of code where I inject a W2 in between the x transpose and the x. So here it is. I've got x transpose W2 x, that whole thing inverted, times x transpose times the weighting matrix times y, and that's my UW. And now let's see what it looks like. All right, so here's a case where the x and the y data don't actually have that much noise. And so the least squares and the weighted least squares in red and green respectively, they're about the same because everything has a tiny little error. And so even though I'm weighting these errors by more, everything is so small it has very little effect. But if I increase the amount of error, what happens? So now look what happens is, first of all, this data doesn't even look close to fitting a line because I added so much noise to the data. But notice that the red line, it's just trying to split the difference. It doesn't even know what to do anymore. It's sort of given up. But look at the green line. It's basically taken some of those extreme points, extreme to the right, extreme to the left, because those both have high distances, and it's saying, that's my home. I'm going to fit my line to those points, and I don't care what's happening here near the origin. You may have a high error, but it doesn't bother me. So there is the difference, and there's no right or wrong answer here. There's no reason, there's nothing I can tell you to say you should use weighted least squares versus non-weighted least squares. It depends on the problem. It depends on what you know about your underlying data, but now you have the mechanism to do that when you want to treat your data differently. All right, so that's it for least squares and weighted least squares, and what I hope you will take from this is not just this, what I think is very powerful and basic tool for doing model fitting, for doing data analytics, but it really is the beginning of much, much more to come. This ability to think about how you fit models to data, least squares and weighted least squares are the beginning. There is total least squares, there is maximum likelihood estimation, there is map estimation, and then you get into these very complex machine learning techniques, but they all sort of have emerged out of these techniques. So I hope that both the underlying techniques and the underlying mathematical concepts, particularly the linear algebraic concepts, will give you the scaffolding to go on from here. All right, thanks very much, everybody, and hope to see you soon.